Welcome to the ONF Spotlight series on 5G Connected Edge Cloud for Industry 4.0 transformation. It's my pleasure to welcome and introduce Nate Foster, who's on the faculty at Cornell University. Principles driving P4 programming language for programming network data planes. And he also brings the rigor of programming languages and formal methods to the networking arena. Today he's going to be talking about verifiable networks. Nate, take it away.
Thanks, Larry. So as you've heard elsewhere in this series, we're in the middle of a big transformation where networks are becoming programmable top-down and end-to-end. And so this is really exciting because we can do things like take the intended behavior of the network, maybe specify it at a pretty high level, and then systematically compile it down onto the elements in our network. And this encompasses the SDN control plane, as well as all the forwarding elements end-to-end from one host to another. But of course, with great power comes great responsibility. And just like we make mistakes in other software domains, we now have new opportunities to add faults to our networks. So there can be bugs in the applications themselves. There can be errors in compilers. There can be errors in the drivers for individual devices. And there might even be hardware bugs that manifest in the wrong behaviors. So the question is, how can we use the same things that make our networks programmable to get some assurance about correctness? And I want you to think about sort of one fundamental question, which is if we sort of freeze time and zoom in on, say, a single packet somewhere in our network, can we understand, whether that packet should be there? If we had this capability, then a lot of the richer properties that we might care about, things like, does my network provide connectivity to hosts? Is it free of loops? Am I waypointing through various middle boxes? Is it resilient? Does it give me isolation? A lot of these things can be reduced to this fundamental question. And it turns out that the answer to this question is being enabled by the shift from protocols to programs. So traditionally, networks were implemented with closed devices that implement things like IETF standards, maybe IP. But nowadays, as we're moving to devices where the protocols are not baked in, we have these programs, and the programs give us some leverage in two ways. So first, because we have a description of how the network's supposed to behave, we can start to bring ideas from programming languages and formal methods to bear on reasoning about those programs. So we can start to ask questions about which packet should be where. And then second, because we have the ability to program the network, we can start to write our programs in ways that will be more likely to ensure correctness. So I want to kind of focus on both of these approaches in this short talk and just give you a taste of some of the ideas that are being brought to build verifiable networks. So broadly speaking, you can split these into sort of static approaches. And here the idea is, because we have a complete description of the network behavior, we have the programs in the control plane, we have the programs in the data plane, we can use ideas like static analysis or formal methods to start to reason about those behaviors automatically. And then the second is dynamic approaches. And I think this is sort of earlier stage work. It's something that's just starting to be done. But here the idea is that we can use programmability to instrument networks. And we can do this instrumentation in a way that collects up observations about behavior, and then we can check those observations against formal specifications. So keep these two broad approaches in your mind as I take you through some technical details. So I'm going to start with static verification. The picture you should have in your mind here is that we have a network, and we can take the elements and model them as programs. I'm going to focus on data planes, but you could apply this more broadly to groups of devices and even things like the control plane. So once you have this program, you can somehow extract from it a mathematical model that captures what it's doing to its inputs and outputs, namely packets. And then if we have some kind of specification of some properties that we care about, we can take that model and pass it to some kind of verifier and either confirm that our specification is satisfied or find that it's not. Okay, so let me give you a very simple example of this in action. I want to zoom in on kind of one forwarding element and just suppose for the moment that we want it to implement a simple access control list, so some kind of firewall. So we've programmed this device, say with the P4 language, and we've configured one of the tables in this program so that it implements an access control list that filters packets going to a given server. And this probably seems like a very simple example, and it is, but it turns out not to be a toy example. There's a nice blog post from the folks at Forward Networks who have been doing static analysis of not just a single device, but of whole groups of devices. And they found bugs exactly where an access control list was implemented the wrong way in some commercial products, and that led to property violations that could break the security stance of an organization. So let me show you now in a little demo kind of how this works. So I'm going to show you some code on the left, and then I'll run this through a static analyzer that we built a few years ago on the right. And I'm not going to give you a full tutorial into P4, but you can kind of get a sense of what P4 programs look like by looking at this code. So as I said earlier, one of the cool things about P4 is that the protocols that we're implementing on the network data planes are not baked in, but they're defined by our program. And so although this program is going to work with standard protocols like Ethernet and IPv4, we actually have to define those. So we start by defining some types, one for Ethernet, one for IPv4, and then we define a packet parser that takes a serialized packet, on the wire, and it populates these structures. Then we get to define the packet processing in terms of actions and tables, so-called match action tables. And in this case, I'm just going to have this whole program implement an access control list. So I just have two actions, allow and deny, and then I have a table that's going to look at, in this case, the IP address and either allow the packet or deny it. And what allow does is it ends up forwarding the packet out on a certain port, and deny just drops the packet. And so there's many properties I could want to show of this program, but the one I'm going to use for a simple running example is, after running this program, it should be the case that either the packet got dropped or it's going to get forwarded out port 1, which was mentioned up here. So let's go ahead and pass it to our verifier. And what you see is that, in fact, this program does not satisfy this property. And we get a little counterexample trace that shows us an example packet and the trace through the program that caused it to fail the property. And in this case, you see the packet was an Ethernet packet and not an IPv4 packet, and then it missed in the table. And so if we miss in the table, then it turns out that the program doesn't actually specify how the packet should be forwarded, and so it may not be one of these two behaviors that we thought we had. And so the way we can fix this is just to add a default action so that even if we miss in the table, we're assured that one of the two actions will be applied, in this case, deny. So if I run this through my program again, then we see that the assertion passes. So this is a very simple example, and really all I'm doing is sort of picking a packet, right after this program runs and checking if it sort of has the behavior I like. But as you can see, there's a fairly low-level detail in the implementation of the program that we got wrong. So I wanted to show you one more example before going back of something a little bit more interesting. So here, I want to actually check that my program is implementing an access control policy that I showed on the slide before. So here I'm going to change my assertion a little bit. And instead of just checking that it either forwards or drop, I'm going to check that actually for a particular IP address, that server in my slide, that actually it is that the access control list drops packets going to that server. And as you can probably guess, the first version of this is not going to satisfy the property because, of course, we can take a packet that has that very address. Here it is written in hex, and we can hit in the ACCO list, which will then cause us to go through. And the reason that that's the case is that although we've made sure that the table will either allow or deny, we haven't actually said what the entries of the table are as populated by the STN control plane. And so if we want to do that, we need some way to specify, let me just bring up the solution here. We need some way to specify the contents of the control plane. And there's various ways we can do that, but the simplest one here is just to assume that when we do a lookup in the table, so when the packet is matched against the entries in the table, if the address is in fact the one we care about, then the action that the ACCL selects will be denied. So think of this as essentially a constraint on the control plane. it must populate the table with a deny rule for this particular address. And so if I run this through, if I've done things right, unsurprisingly, it passes. So again, this is a very, very simple example, but it shows you some of the power we have from being able to specify data plane behavior in a program and then start to do automated reasoning about it. So how does this work at a technical level? So under the hood, we use a fairly standard set of ideas from program verification. So we take our source program, you see on the top of this diagram, and we annotate it with assertions. Those assertions can be written by the programmer. We also have some support in our tool for automatically adding assertions if you don't want to write logical formulas. And then we actually translate the P4 program into a standard imperative representation. Think of it sort of like C. And then we apply some standard optimizations and transformations, and we generate a logical formula that we can pass off to a theorem prover. And the theorem prover then either is able to show that that formula is valid, or if not, it gives us a counterexample, which we can map back to a trace. So this gives us a really detailed way to model the behavior of a P4 program and analyze it really in arbitrary ways at right down to the bit level. So how well does this work? You can apply this, of course, to small programs and toy programs, but we also applied it to very large programs. So this is an evaluation we did a couple years ago, where we took switch.p4, which is a big, roughly 6,000 line P4 program that models the capabilities of a typical top-of-rack switch. It has about 58 parser states, 120 tables. And we actually verified an end-to-end property showing that the program satisfies some key safety properties, namely that all values that are being read and written by the program are well defined. And to do that, we had to write down an assumption for what the control plane was going to do. It turned out to be this roughly 750 line sort of interface, we call it. And we also found a number of bugs in the program. So bugs where the parser was not correctly recognizing the right protocols, as well as some internal invariants within the program that were not satisfied. So the upshot here is that you can apply this at scale to real programs, and it's a useful tool. It also scales pretty well. So I won't claim that we've pushed this as far as you can go in terms of making it fast. But even with sort of modest engineering, we've been able to apply this to a large number of programs and get verification times that are often under a second, sometimes taking tens or hundreds of seconds for very large programs. Okay, so that's all I want to say about static verification. I now want to shift to dynamic verification. To motivate this, I want to sort of highlight a limit of static verification, which is, if you go back to this picture we had before, you can kind of divide this picture in two. On the left-hand side, you have the real operational network, the controller, the data path, and the packets flowing through it. And the whole game we played with static verification was to view this as a big kind of program and then extract from it a mathematical model where we could go off and do some reasoning. So we kind of have these two universes, and there's kind of a strict partitioning between them. And so, if we've done our job right, then the operational side and the logical side should be sort of consistent with each other. And anything that we reason about in the logical side should tell us something about the operational side. But of course, there can be a gap between the model that we extract on the operational side and reality. For example, if our P4 compiler or the driver or the hardware has a fault, then we'll essentially be reasoning about some model that doesn't actually conform to reality. So another idea, and one that a number of us are just starting to pursue, is to look at runtime verification. So here's a different take to verifying properties that, first of all, doesn't require extracting a model. It doesn't require using a theorem prover. And instead, what we do is take the same specifications. We have to compile those into what I'm calling local predicates. So think of these as local checks on a given element for its behavior. And then we actually wrap the components, those elements with a reference monitor that checks for violations of the properties. So as an example of the kind of thing you could do with runtime verification, if you wanted to make sure that two segments of the network were being isolated from each other, you could compile that into local checks where each element is tasked with enforcing that isolation property. And if you ever saw a packet that was about to violate the isolation property, then your reference monitor would detect that the packet was going from one segment to another and drop it, preventing that from happening. So this is a very general idea. It's, reference monitors and runtime verification is not a new technique. But what's nice about it is it's very simple, and it also is more connected to the operational reality of the network, because you're actually observing the behavior rather than verifying some model of the network. And then another approach to runtime verification, which I think is sort of a second step, is to actually fuse more closely the observations about the data plane with decisions being made about the control plane. So we have this slogan of verifiable closed loop control. And the ingredients here are to use programmability to actually collect observations about the network. So think of this as being telemetry data. And as the network is generating all these telemetry traces, we can verify those. So we could play the same game I showed you on the last slide with using a runtime monitor to check for properties. But we can also feed those observations back into the control loop to give us information about how we might actuate the network in order to achieve some global objectives. So I think these sort of two takes on runtime verification are a pretty exciting direction that is low effort for programmers. You don't need to be a logician to use them. They're very connected to the operational side of the network. And because they closely couple the data path and the control plane, they have a kind of comprehensive nature to them, which I think is quite attractive. There are a bunch of open questions. So one question that you should always ask with runtime approaches is, isn't there a cost to this? And indeed, if you're verifying networks by collecting observations about behavior and then verifying those, you're adding extra overhead. The collection, serialization, and transport of those records cost something. So can we find ways to reduce the amount of data we have to collect, and also to do the checking in line so that we don't need to move lots of data around just for the purposes of verification. Another big question is expressiveness. So it's pretty obvious how you could use runtime techniques to check for kind of properties that are already local. Does this device correctly filter certain kinds of packets? But if you talk to network operators, they're interested in not just kind of device level input-output behavior, but richer properties that talk about either multiple elements or aggregate behaviors. So can we use these runtime techniques to talk about things like quantitative properties and quality of service? Can we reason about causality and properties that involve multiple elements? It is possible, but some work is needed to figure out how to bridge the gap between these kind of local predicates and these broader network-wide views. And then the third piece is about trust. So runtime verification in particular, and the version where we're actually doing the checking in the network, means that we're using the same elements both to implement the forwarding behavior and to do verification. And so if that's going to be effective, in particular, if we're going to use this to guard against maybe a malicious attacker or a hardware fault, we need there to be some independence between the system that we're checking and the checker itself. And so coming up with ways where we can detangle these two and know that the conclusions that are being produced by the verification infrastructure are sufficiently trustworthy is another area. Okay, so I'll stop there, I think, and let me thank my collaborators at Barefoot, Stanford, Yale, and others, and point you to my webpage if you want to read more about these systems. Thanks.
Thanks, Nate. Thanks. Let me go back actually to the point that you raised on your next to last slide there about efficiency. I heard the phrase theorem prover earlier on in your talk, And you said you haven't really spent time optimizing there. Can you just give us a sense of why you're optimistic that you will be able to address the efficiency issue in the dynamic runtime checks?
Yeah. So there's a couple of reasons. Uh, One is that, of course, we have choices about at what granularity we want to verify. So maybe one way to think about this is you could think of the network as implementing some kind of function, some kind of transfer function. Packets come in and packets go out. And so one way you could verify a property is basically to build sort of a second copy of that. Maybe the second copy is derived not from a compiler and a driver and and a piece of hardware, but from maybe a high-level intent. And then you basically check that those two things agree with each other. Um, so in general, the two copies of the function, the one that you're running and the one that you're checking, may have the same size. But if you're willing to do the checking maybe in fewer places or on a subset of the packets, or maybe you do some kind of probabilistic checking, you have a dial that you can use to reduce that cost. And this is not a new idea. People who have worked on, say, path validation on the internet have used similar techniques to gain assurance about correct forwarding paths with limited resources. Another idea is one that's also been explored in the software domain, is the idea of inlining reference monitors. So this is work that I'm most familiar with from some colleagues at Cornell who looked at runtime monitors for Java programs way back like 20 years ago. And the idea is that if you take a system and you wrap it with a reference monitor, you add some overhead. But if you have a compiler that's aware that the system that you're monitoring and the monitor itself, that is doing that, it may be able to optimize the checks and the program. And by doing an analysis of the code, it may be able to sort of push the checks deeper into the program and therefore reduce their cost. And so in the case of Java, people like Fred Schneider and Ulvar Erlingsson were able to bring the cost down pretty dramatically. And I think the same idea here could be brought to bear on runtime verification of P4 programs. So if we take the runtime monitor and we combine it with the P4 program, then many of the checks that we might do and many of the state that we might collect can essentially be optimized away. Now it does raise a question about the trust bullet, because if you're doing the inlining, you need to trust that your compiler is doing the right thing. But if you have a reason to trust your compiler, I think that those costs can be brought down.
Yeah, the monitor idea sounds really, really powerful. I'd also like to go back to where you started, which is for someone that like myself that's been in this industry for a long, long time. The old days of here's your protocol spec comes down from the IETF or wherever, and you go off and start writing a bunch of C code. Now you're suddenly shifting to a world where you're using this domain-specific language P4. First of all, I can imagine people thinking, I write my programs in C. I don't write them in P4. Could you talk just a little bit about the power that benefits that a language like P4 brings to someone that hasn't really thought about it before?
Yeah. So I don't want to claim that we're going to write all of our network software in P4. That's clearly not the case. But what I'm excited about is the idea of at least specifying, say, the packet formats in an executable form. I think that's something that is well within our technical grasp, and it has benefits because it just sort of removes a layer of sort of fog if you want to build tools. For example, if RFCs came with, instead of a little ASCII art diagram, laying out the protocol format, but actually a P4 program that you can run, that gives you sort of a golden standard that you could at least check the formats against. Now, I'm well aware that real protocols, especially complex protocols like say Quick or something, you want to write the specifications in a way that are loose enough to accommodate multiple implementations, and that's why the IETF sort of has worked the way it has so successfully for many decades. And I don't mean to demean that at all. But if you also have a executable sort of reference implementation of the protocol itself in a restricted language like P4 instead of C, so where that's possible, then the fact that the language is so restricted makes it more amenable to verification. So I have to go a little bit on a deep dive here, but like, verifying C is very possible. And there are, there's a whole industry of static analyzers now that can work for, large C programs. But a lot of work has to go into, abstracting away details or dealing with things like complex data structures and pointers and loops. And so P4 just doesn't have those things. P4 has a relatively simple data model. It's mostly loop-free. And so you don't need to sort of bring out the heavy machinery in order to get a scalable and precise reasoning tool. You sort of do a fairly straightforward application of ideas from verification, and you can build a logical model, and then you can start to ask questions with a theorem prover, again, right down to the bit level. So I think it's not a question of either or, but it's sort of like when you have a simple behavior that can be specified in DSL, I think sort of why not? Because then you can
as you would in a switch that's trying to forward packets at terabits a second. So
exactly, yeah.
Yeah. So the counterpart is there's still going to be, as you said, there's still going to be a lot of C code out there, and especially or C or whatever Java up in the control plane. And it was interesting to hear you talk about checks that you can do. There's an assume statement in your P4 program example earlier on that are basically control data plane checks that the control plane is behaving correctly, if I understood that right. Just generally, could you talk a little bit about how much we can do in the control plane?
Yeah.
Or verifying the control plane.
Yeah, so I'll tell you what I think is the most promising approach. I think there's other approaches you could take. For me, what makes this a kind of intellectually fun place to be is that although data paths are pretty simple and in some ways sort of degenerate almost, like a verification person would say this is sort of too simple to be interesting. You have this missing piece, which is the control plane. And so the interplay, if you want to get an end-to-end property about a whole system, in most cases, you can't just take the trivial, hardware pipeline inspired program. You need to also know something about the control plane. And so that assume statement was basically, expressing a constraint between the missing piece. And I think that this is super interesting. Sort of how do you do verification with sort of unknown code? And so one thing you do is you can basically just specify, well, the unknown code does something, I don't know what, but it had better, populate my tables with these entries. And that's basically what I showed you. But there's other things you could do. For example, you could figure out, what's the weakest constraint I could make on the control program that would suffice to prove my property. And there's some really nice work out of Bucharest, Kostin Reku's group at SIGCOMM last year. They built a system called BP4, where they did this. So they had some heuristics, and they could basically figure out what are some weak constraints on the control plane. So that automates the task of writing down these interfaces. More broadly, I think we should reach up into the control plane, and there are certainly relatively low-level abstractions that I think would be amenable to analysis. So if you take an SDN controller, for example, that knows something about intents, these are pretty high-level declarative things, like I want these kinds of machines to have connectivity to these kinds of machines, or I want this kind of resilience. So that's very straightforward to model. Are we going to verify hundreds of thousands of lines or millions of lines of code, full stack control plane? Maybe someday, but I think that's still a long ways off.
Great, thanks. So this was a great talk. I learned something, and that's always a good thing. So thanks a lot, Nate.
Great.
Thank you.
Thank you.